Hello students, welcome to Educate. Today we are going to start chapter number 8 of class 12 physics. So here the chapter name is Electromagnetic Waves. First of all, we will see what is displacement current. So if you consider a circuit in which this is capacitor and there is source here. So what happens while charging? Current will flow like this, right? But there is one question. If there is no connection between these two plates of a capacitor, then how current is continuous? Here, if current IC, say conduction current, is flowing like this, so from this plate the same current comes out, but here there is break. If you remember, if we consider a circuit like this and here there is break, here suppose wire is cut, then will current flow or not? Current will not flow, but here current is flowing. So what is happening? So here in between these plates, is there some current, and how it is flowing without medium? So of course there is one current in between these two, and that will be called displacement current, ID, and we will prove it that it is also equal to IC, right? So here where there is no conducting wire, so due to changing electric field there will be another current that will be called displacement current. So when we write equation integration b dot dl, so this will be, earlier it was mu naught I, but now it will change to mu naught IC plus ID, right? So this will be modified Ampere circuital law. So here we are going to see that IC equal to ID. So if you remember, phi E equal to EA cos theta, here theta is taken to be 0 degree, which can also be written as Q upon epsilon naught A times A, which is Q upon epsilon naught. This is Gauss theorem, if you remember. And now if we find d phi E divided by dt, what do we get? D upon dt of Q upon epsilon naught, right? So what do we get further? So 1 upon epsilon naught dq by dt, and you know dq by dt is equal to I, which is conduction current. So we can say epsilon naught times d phi E by dt is equal to I. So here this I will be denoted as, I will be written as ID, displacement current. So this is expression for displacement current. Now here same thing is written as I told you, Ampere circuital law, integration b dot dl is mu naught I plus ID. Here IC you can write conduction current, this as ID, and then put the value of ID. So this will become mu naught IC plus mu naught, and ID we have already found as epsilon naught d phi E by dt, right? So this is also known as Ampere Maxwell law. Right. Now let's see further. Here some important results are written. This is Gauss law of electricity that you have studied, that integration E dot ds or E dot dA gives Q upon epsilon naught, that is measure of flux. Then integration B dot dA, Gauss law for magnetism, this gives 0, means net flux will be 0 in this case. And Faraday's law, you have seen that change in flux with the time gives EMF induced. And then recently we have studied that integration B dot dl gives mu naught IC plus mu naught epsilon naught d phi by dt. So you have understood. Now we are going to see electromagnetic waves. So if there is accelerated charge, then it will give rise to electromagnetic waves, and the speed of electromagnetic waves is c equal to 3 into 10 to the power 8 meter per second, irrespective of the wavelengths, means all the colors have same speed, right? Here some more information is given that you can read. Now we will see representation of these waves. So electromagnetic waves, here this picture shows that this is x-axis and this is y-axis, this is z-axis. So wave is propagating in z-axis, electric vector is along x-axis, magnetic vector is along y-axis. So all three must be mutually perpendicular. So here equation we can write Ex, as you have seen, electric vector is along x-axis. So Ex equal to E0 sine kz minus omega t, where k is propagation constant. We will study about it. Omega is angular frequency. Similarly, if we write expression for magnetic field, so that will be By equal to B0 sine kz minus omega t, and k is given by 2 pi by lambda. So we will see speed of electromagnetic wave is given by c equal to 1 upon square root of mu naught epsilon naught, and this will be 3 into 10 to the power 8 meter per second, right? And the relation between E and B, so let's write their maximum values. So E0 electric vector will be C times B0, or C is E0 divided by B0. So you can say total electric field means maximum value of electric field divided by maximum value of magnetic field gives the speed of light, or EM waves. And if relative permeabilities are given, like relative permittivity epsilon and magnetic permeability mu, in that case speed, we are talking about the speed in medium, so one will be this will become mu and epsilon, right? Now we will see different spectrums, but before that let's see these questions. Question says a plane electromagnetic wave of frequency 25 million hertz travels in a free space along the x direction at a particular point in space and time E equal to 6.3 J cap volt per meter. What is B? As we have studied that ratio of E to B gives C. So here We have to find out B. We are given E. So E divided by C will give value of magnetic field. So that comes out to be 6.3 divided by 3 into 10 power 8. That gives 2.1 into 10 power minus 8 Tesla. Right? And since all three are mutually perpendicular, if direction of propagation of wave is given, wave is propagating along x direction, electric vector is along j direction, means j means y axis, then obviously magnetic field will be along z axis, that is with k cap. Right? Now consider another question. Next question says the electric field in a plane electromagnetic wave is given by By equal to 2 into 10 power minus 7 Tesla sine 0.5 into 10 power 3 x plus 1.5 into 10 power 11 t. Here you have to consider the basic equation B equal to B0 sine either omega t plus kx, here kx plus omega t, where k is 2 pi by lambda and omega is 2 pi by t. We can compare to get the values. Like B0 we can easily find this is 2 into 10 power minus 7. From here we can evaluate E0. E0 will be C times B0, right? And here kx 2 pi by lambda is k, so here 2 pi by lambda is given this much, so we can find lambda, and this is omega t, so 2 pi by t equal to this much, so we can get omega. So same thing is being done here. Other way around, if you want to write, this can be written, but that is better way. Means if you write standard equation like B equal to B0 sine, here just write 2 pi by lambda x plus 2 pi by t into small t. And if you compare, so you will get this value as 2 pi by t, from where t can be found. If you write this value, you can compare it by 2 pi by lambda, and the first value, this is equal to B0. So you will get all values, and when you have got 1 upon t, that will be frequency. So this, I think, thing is clear. And now suppose you want to write the electric vector. So electric vector magnitude will be this much. If you want to write the equation, if they have asked, so the corresponding equation you can write E equal to E0 sine, rest thing will remain same. Only the value of E0 will change, that will be equal to 2 into 10 power minus 7 times speed of light. So that you can write. So here this is given. Understood? Now electromagnetic spectrum means we are going to see different type of waves and their corresponding wavelengths. So here spectrum is shown. Here frequency is given like gamma rays 10 power 23 to 10 power 19, and the corresponding wavelengths are given 10 power minus 14 to 10 power minus 11. Then comes X-rays, then ultraviolet, then visible, then infrared, then microwave, then short wave, then television and FM radio, then AM radio, then long waves. Right? Here spectrum of visible light is analyzed in violet, then blue, green, yellow, orange, red, etc. Right? Now some properties of different type waves are given, like here radio waves. Radio waves are produced by the accelerated motion of charges in conducting wires. They are used in radio and television communication system. They are generally in the frequency range from 500 kilohertz to about 1000 megahertz. The AM amplitude modulated band is from 530 kilohertz to 1710 kilohertz. Higher frequencies up to 54 million hertz are used for short wave bands. TB waves range from 54 megahertz to 890 megahertz. The FM frequency modulated radio band extends from 88 megahertz to 108 megahertz. Cellular phones use radio waves to transmit voice communication in the ultra high frequency UHF band. How these waves are transmitted and received is described in chapter 15. So this point is not in your syllabus now. Means chapter 15 is omitted. Then comes microwaves. Microwaves like short wavelength radio waves with frequencies in the gigahertz range are produced by special vacuum tubes called klystron. You should remember this point how microwaves are produced by klystron, magnetron, and gun diodes. Due to their short wavelengths, they are suitable for the radar system used in aircraft navigation. Radar also provides the basis for the speed guns used in time fast balls, tennis serves, and automobiles. Microwave ovens are an interesting domestic applications of these waves. In such oven, the frequency of the microwaves is selected to match the resonant frequency of the water molecules so that energy from the waves is transferred efficiently to the kinetic energy of the molecules. This raises the temperature of any food containing water. This is important concept. You should understand how the thing put or how the food put inside the microwave get heated. Then comes infrared waves. Infrared waves are produced by hot bodies and molecules. This band lies adjacent to the low frequency or long wavelength and end of the visible spectrum. Infrared waves are sometimes referred to as heat waves. This is because water molecules present in the most material readily absorb infrared waves. Many other molecules, for example CO2 and H3, also absorb infrared waves. After absorption, their thermal motion increases, that is, they heat up and heat their surroundings. Infrared lamps are used in physical therapy. Infrared radiation also plays an important role in maintaining the Earth's warmth or average temperature through the greenhouse effect. Incoming visible light, which passes relatively easily through the atmosphere here, which passes relatively easily through the atmosphere, is absorbed by the Earth's surface and radiated as infrared, longer wavelength radiation. This radiation is trapped by greenhouse gases such as carbon dioxide and water vapor. Infrared detectors are used in Earth satellites both for military purposes and to observe growth of crops. Electronic devices, for example, semiconductors, light emitting diodes, also use infrared and are widely used in the remote switches of household electronic systems such as TV sets, video recorders, and hi-fi systems. Then comes visible rays. It is the most familiar form of electromagnetic waves. It is the part of spectrum that is detected by the human eye. It runs from about 4 into 10 power 14 hertz to about 7 into 10 power 14 hertz as a wavelength range of 700 to 400 nanometer. Visible light emitted or reflected from objects around us provides us information about the world. Our eyes are sensitive to this range of wavelengths. Different animals are sensitive to different ranges of wavelengths. For example, snakes can detect infrared waves, and the visible range of many insects extends well into the ultraviolet. Now comes ultraviolet rays. You have already studied about it. It covers wavelengths ranging from 4 into 10 power minus 7 meter, 400 nanometer, down to 6 into 10 power minus 10 meter, 0.6 nanometer. Ultraviolet radiation is produced by special lamps and very hot bodies. The sun is an important source of ultraviolet light, but fortunately, most of it is absorbed in the ozone layer in the atmosphere at an altitude of about 40 to 50 kilometers. UV light in large quantities has harmful effects on humans. Exposure to UV radiation induces the production of more melanin, causing tanning of the skin. UV radiation is absorbed by ordinary glass, hence one cannot get tanned or sunburned through glass windows. Then comes next point, welders wear special glasses, goggles or face masks with glass windows to protect their eyes from the large amount of UV produced by the welding arcs. Due to its shorter wavelengths, UV radiations can be focused into very narrow beam for high precision applications such as LASIK, laser assisted in situ keratomelusis. This point you have to remember the full form. LASIK, laser assisted in situ. In situ means in same place. Then keratomelusis. This is type of eye surgery. Then UV lamps are used in killing germs in water purifiers. Then comes ozone layer is in the atmosphere plays a protective role, and hence its depletion by chlorofluorocarbons, CFCs, gas such as freon is a matter of international concern. Then comes this chapter is completely based on theory. So then comes X-rays. Beyond the UV region of the electromagnetic spectrum lies the X-ray region. We are familiar with the X-rays because of its medical applications. It covers wavelengths from about 10 power minus 8 meter down to 10 power minus 13 meter. One common way to generate X-rays is to bombard metal target by high energy electrons. X-rays are used as a diagnostic tool in medicine and as a treatment for certain forms of cancer. Because X-rays damage or destroy living tissues and organisms, care must be taken to avoid unnecessary or overexposure. Then last comes gamma rays. They lie in the upper frequency range of the electromagnetic spectrum and have wavelengths of from about 10 power minus 10 meter to less than 10 power minus 14 meter. This high frequency radiation is produced in nuclear reactions and also emitted by radioactive nuclei. They are used in medicine to destroy cancer cells. So here we will see one table in which type of waves, then wavelengths, their production and detection. This table is important for you for your exam. Like a radio wavelength is greater than 0.1 meter, and production rapid acceleration and deceleration of electrons in areals, and detection can be done by using receivers areals. Then comes microwave wavelength 0.1 meter to 1 millimeter, and production is done in klystron valve or magnetron valve, and detection can be done by point contact diodes. Then comes infrared. So wavelength is 1 mm to 700 mm, and production vibration of atoms and molecules, and use thermopiles, bolometer, infrared photograph film. Then comes normal light. So 700 nanometer to 400 nanometer. Electrons in atoms emit light when they move from one energy level to lower energy level, and so detection can be in the eye, photocells, photographic film. Then comes UV rays, 400 nanometer to 1 nanometer. Inner cell electrons in atoms moving from one energy level to lower energy level, and detection can be done by photocells, photographic film. Then comes X-rays, 1 nanometer to power minus 3 nanometer, X-ray tubes or inner cell electrons, and detection, photographic film, Geiger tubes, ionization chamber. And last one is gamma rays, whose wavelength is less than 10 power minus 3 nanometer, and production is radioactive decay of the nucleus, and detection is photographic film, Geiger tubes, ionization chamber. So this was the summary of the lesson, and then a quick recap of the things that we have studied. Maxwell found an inconsistency in the Ampere circuital law, that is integration B dot dl equal to mu dot I. Between the plates there is no current, still circuit is completed. Then how? And suggested the existence of an additional current called displacement current to remove the inconsistency. This displacement current is due to time varying electric field and is given by ID equal to epsilon naught d phi by dt, and acts as source of magnetic field in exactly the same way as conduction current. Then second point, an accelerating charge produces electromagnetic waves. An electric charge oscillating harmonically with frequency nu produces electromagnetic waves of the same frequency nu. An electric dipole is a basic source of electromagnetic waves. Third point, electromagnetic waves with a wavelength of the order of a few meters were first produced and detected in the laboratory by Hertz in 1887. He thus verified a basic prediction of Maxwell's equations. Then comes fourth point, electric and magnetic fields oscillate sinusoidally in space and time in an electromagnetic waves. The oscillating electric and magnetic fields E and B are perpendicular to each other and to the direction of propagation of the electromagnetic waves. For a wave of frequency nu, wavelength lambda, and propagating along z direction, we have the equation E equal to ext, which is given by E0 sine kz minus omega t. We can further write E0 sine 2 pi z upon lambda minus bt, or E0 sine 2 pi z upon lambda minus t upon capital T. Similarly, B can be written as B by T. This is along y-axis. B0 sine kz minus omega t. We can further convert B0 sine 2 pi z upon lambda minus Bt, or B0 sine 2 pi z upon lambda minus t upon t. And you know the relation E0 upon B0 gives speed of light. And the speed of light in vacuum is given by C equal to 1 upon square root of mu naught epsilon naught. And light in electromagnetic waves C is therefore also the speed of light. Here electromagnetic waves other than light also have the same velocity c. Now in medium V will be given by 1 upon square root of mu and epsilon, where mu is permeability of the medium and epsilon is permittivity. The spectrum of electromagnetic waves stretches in principle over an infinite range of wavelengths. Different regions are known by different names like gamma rays, X-rays, ultraviolet rays, visible rays, infrared rays, microwaves and radio waves in order of increasing wavelength from 10 power minus 2 angstrom or 10 power minus 12 meter to 10 power 6 meter. They interact with matter via their electric and magnetic fields, which set an in oscillation charges present in all matters. The detailed interaction and so the mechanism of absorption, scattering, etc. depend on the wavelength of the electromagnetic waves and the nature of the atoms and molecules in the medium. So this was the basic theory. Here there are certain points that you must consider, like the basic difference between various types of electromagnetic waves lies in their wavelengths or frequencies, since all of them travel through vacuum with the same speed. Consequently, the waves differ considerably in their mode of interaction with matter. Accelerated charged particles radiate electromagnetic waves. The wavelengths of the electromagnetic wave is often correlated with the characteristic size of the system that radiates. Thus, gamma radiation having wavelength of 10 power minus 14 meter to 10 power minus 15 meter typically originate from an atomic nucleus. X-rays are emitted from heavy atoms. Radio waves are produced by accelerating electrons in a circuit. A transmitting antenna can most efficiently radiate waves having a wavelength of about the same size as the antenna. Visible radiations emitted by atoms is, however, much longer than the wavelength than atomic size. And finally, infrared waves with frequencies lower than those of visible light vibrate not only the electrons but entire atoms or molecules of a substance. This vibration increases the internal energy and consequently the temperature of the substance increases. This is why infrared waves are often called heat waves. And the center of sensitivity of our eyes coincides with the center of the wavelength distribution of the sun. It is because humans have evolved with a vision most sensitive to the strongest wavelengths from the sun. So this is how lesson is over. Thank you for watching. Team Educate.